Okay, so today we're going to talk about exponents, logs, this number e, and ln x. Okay, so to set it up, let's consider a crazy bank is offering to pay 100% interest, which is never true, but let's just consider it. Interest per annum, okay? If the initial investment of $1, find the value of the investment after 1 year of interest, if it's compounded yearly. Well, if we remember our formula for compound interest, I know I take my principal, and it's 1 plus the interest rate, it's 1 plus r, over n, the number of compound periods, and then n times the number of years. Well, if we take this scenario, I'm going to take my initial value is 1, and 1 plus my interest rate in this case is going to be 100%, dividing it by n, which is n, and n to the t. And so for this particular example, yearly n is going to be 1. And when I look at the next one, monthly, n is going to be 12. When I look at weekly, n will be 52, daily to be 356, and so on and so forth. So I'm going to put this into Desmos to compare all these different scenarios here. And I'm only going to do it for 1 year actually. So I'm going to do it for 1 year. So t is actually equal to 1. So I can get rid of that as well. And so if I do these values, let's take a look here. So here is my equation. I've already set it up. And so if it's $1 for 100% for 1 year compounded per year, that will become 2. If I go for 12 months, I would now have 2.6. If I would go for 52 weeks, I would have $2.69. If I would go for 365, I get 2.71. And then it asked me to go continuously, which I can't really do, but I can start to make larger numbers. So what happens if I go 1,000, or if I go 10,000, or 100,000, or 1,000,000? What do you notice if with the interest, it eventually starts to go to a limiting value of a sort. And so it doesn't continue to grow forever. It just eventually goes to this value here, 2.71828, and so on. And so that is compounding continuously. And that number is a brand new number, and it's called E. It's Euler's number. He has his own number, and it is approximately 2.71828. 1828. It is like pi in the sense that it is an irrational number, and it goes on forever and ever and ever, infinite decimal places. And the definition of E is if I take 1 plus 1 over n to the power of n, and I make n go to infinity, that will equal to E. Okay, and this is a famous number. It's used extensively in biology. Anything where there's compounding is often seen. All right, so now we have this brand new number E. If I go to my calculator, I can go E to the power x to the power 1, and I can see the value. Or I can also see E. I can just have straight E here, and then I can put the power as I wanted. So there's 2 ways to get to E. Okay, so if the investment rate, written as a decimal, is R, and our compounds per year on the investment of $1 for t years, write an equation for the future value. Well, the future value of that is going to be my $1 and 1 plus r over k to the to the k t. That's the formula for future value. Okay, but if I want an investment to go continuously, that means k is going to infinity. That means that's going to be 0, which I don't really want. Show that the investment can be written as e to the rt. And here's a hint. We're going to make m equal k over r. So if I take 1 plus, well, this is r over k. If I want k over r, I can rewrite this as 1 over k over r to the, well, k I can see here, if I multiply, is equal to mr, and so I can say that this is equal to 1 plus 1 over k to the r, and k is equal to m times rt. Well, if I do some substituting here, I know this is 1 plus 1 over m, just some variable that relates k and r, is equal to m to the rt. Now, as k goes to infinity, I know then that also m goes to infinity. Because if k gets really, really big, it doesn't matter what r is, m will get really, 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 really big. And so then, what I can say then is that this here, this part here, that is e. So I can rewrite this as 1 plus 1 over m to the power of m. All of that is to the power of rt using my exponent rules. This inside is e, and so it's e to the rt. And so if something is going to compound continuously, I can use this idea here. And so the formula that exists is the original amount times e to the rt is equal to the current principal. Okay, and I often refer to this as PERT, because it says PERT, the PERT formula. And we're going to talk about this particular formula for modeling at a later time. But this is one of the most useful ideas behind E.